Good morning or good afternoon, depending on where you are. My name is Professor Duke Orata. We are continuing with our lectures in thermodynamics, and today we want to look at three-dimension steady-state conduction. Steady-state heat conduction. Well, we have talked significantly about heat transfers in our other lectures, and I keep encouraging you to go through them to help you be up to date with each and everything we are doing. And today we want to look at three-dimensional steady-state conduction in systems. Remember, when we were dealing with one-dimensional heat transfers, then the temperature change was along the direction of the heat flow. The temperature change was considered along the direction of the heat flow. And we assumed that those planes or surfaces which were normal to this direction of this flow were isothermal. In other words, the temperature was the same throughout. That is not the case with three-dimensional case. One, we want to think of three-dimensional case as we are dealing with a temperature field. We are dealing with a temperature field. So we are not dealing specifically with temperature change in the direction of the heat flow. So one of the things which we need to do is that the material which we are dealing with must be homogeneous. And when we are thinking of homogeneity, we are saying that it's specific heat, its density, and thermal conductivity should be constant. So the material should be homogeneous. And the other thing is that we want that this particular system we are dealing with, the material must be isotropic. In other words, whichever property you choose, that property should be the same in all directions. So when we are talking about the three-dimensional conduction, we are going to focus on elemental areas or volume elements for that matter. We'll draw them in the form of volume elements, but we are looking at the elemental areas. So let us look at our first profile. So we consider, let us focus on volume elements. We can call them sigma A1, sigma A2, or basically we can say sigma AI, where A is area. So we are talking about elemental areas. We are going to focus ourselves on those elemental areas. So that in a nutshell, if we take, for example, let's take this schematic here. Let's take this schematic here. Let it not be too big so that it doesn't occupy much space. Let's just try to limit it. Let's call that DZ. Let's call that let's call that dx. Let's call this dy. Let's see if I've gotten it wrong. Not the best. 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 Let's see. Yeah, that's reasonable. So we have dz, dy, dx, we have dz, and we have dy. So let's just leave it at that. dz, dx, dy. And so if we transpose it in the Cartesian coordinate, then this will be our z-axis, this will be our x-axis, and our y-axis. So we've just transposed it to the Cartesian coordinate system. Now, when we are dealing with steady state heat flow, we are assuming that the heat which flows into this system, the heat which flows into this system, and the one which comes out of this system are under steady state conditions. And you know, when we talk of steady state conditions, you know we are talking of no accumulation of energy, no accumulation of material, the rates being constant, and so forth and so forth. So let us look at this system. Let us say that the heat flows into this particular system. Let's call it dq. Let's call it dq1 of x, because it's moving along the x-axis, and then what comes out, let's call that dq2x. Let's call that dq2x. So when we use the Fourier heat law to establish the rate of heat transfer in that particular system, so applying the Fourier heat law, remember that the Fourier heat law, the rate of heat supply, the rate of heat transfer is given by those quantity, the quantity there, that is the temperature gradient that is the area of flow, that's thermal conductivity, and this is the rate of heat flow. I'll put that dot, that's using the notation that is dq over dt. That notation, just put it there so that you familiarize yourself with it always. Now, so applying the Fourier's law to this particular phase here, remember this particular phase here is dz and dy. dz and dy. That element of area there is dz by dy. So for dq, one x, we have minus k dy dz, that element of area, remember, dz times dy, that gives us that area, that element there, which I'm going to mark then the change in temperature with X for the axis. And the heat coming out, flowing out, the heat out of that system is dq 2x, cumbersome notation, dq 2x will be minus k dy dz into d dx into t plus del t del x dx. Think of it simply in your mind that what we are saying is that there is some change in temperature which is represented by del t. If you cancel this quietly in your mind, dx by dx then is t plus dt. There's some change in temperature. There's some change in temperature. So that this basically is minus k dy dz del x d x of t plus del squared t squared del squared t del x squared dx. And so if we go to the other element of area, let us go to the other elemental area. So we have covered this particular area, then we'll cover the other faces. So let us look at the symmetry which comes out. We are looking at the heat along the x-axis, so we are left with the elemental area dy by dz. So when we'll be on y, definitely we'll be left with, when we are on y, we'll be left with dx and dz. When we are on z, we will be left with dy dx. So that's a symmetry. You need to get a mnemonic of remembering things. You have to have a mnemonic of remembering things because each of the things have a pattern. A lot of the things are linear and they are patterns. Non-linear cases are there, but majority of things are linear and you can see a pattern coming out. So let us take the other one, dq 1 y along y-axis, like we have said, for the x, so we have that elementary area dy by dz. So for the y, we'll have that for dx by dz. That is, we'll be dealing with this area here, dx by dz. Now, in other words, the heat flowing in that direction. So we have minus k, that will be dx dz del t del y, it's along y, and then out, heat flowing out to y minus k dx dz d del y into t plus del t del y dy, which again will now be minus k dx dz del t del y plus squared del y squared dy. And of course, the final phase which you want to look at is now dq 1 z. And like you have said, the moment we see z, we are left with dy and dx. So we are dealing with this particular one, dy, this particular face here. We have our y, we have our x, we have our x there, so we have our y, we have our x, we are dealing, so we have looked at dy, dz, we have already looked at dx, dz. Now we are looking at, we are at y, we are at z, So we are looking at dy, and dx, the direction, coming in, coming out. So we will have minus k dx dy del t del z, and then dq of 2z be minus k dx dy d del z into t plus del t del z dz, which will be minus k dx dy del z del t del z plus squared del z squared dz. So we're in good shape. I repeat, when you're dealing with three-dimensional heat conduction, we are not talking of just heat being the temperature change along some one axis. Now we are dealing with a temperature field. Temperature field. Very important for us to note that. Now, let us look at the changes. The total changes. So we have dq 1x minus dq2x, that becomes minus k dy dz del t del x minus, that is the difference between this and that, minus, so that becomes plus minus k plus, or becomes minus, so we have minus that, that becomes plus k dy dz into del t del x plus del squared t del x squared dx. So let us see how we can simplify this the best way possible. You notice that that will cancel with that. When you multiply k dy dz, this one, that will cancel with that. So you are left with minus k del squared t del x squared dx. Similarly, for dq, 1y minus dq 2y, dq 1y minus, that will be minus k dx dz del t del y plus k dx dz del t del y plus, we now don't need this, we now don't need it, that can go now, that can go, we don't need it. Where are we? Del t plus del squared t del y squared dy. Again, minus k dx dz, remember that is an area element, area, that's area. The t will cancel with that, so we'll be left with, so we don't need this, we don't need this, we have already used it, so it won't affect us. So that will be left with minus k del squared t del y squared dy. So the last one is going to be, the last one will be for z, which we have unfortunately already erased. So dq 1z minus dq 2z, that will be minus k, also will be dx dy del t del z plus k dx dy into del t del z plus del z squared dz. And of course again that will cancel that, and we'll be left with the expression here where we have, that will be minus k, we'll have minus k, we had forgotten to put dx dy there, there's a dx dy, that will be minus k dx dz. Let's make sure we have not missed out that will be minus k dy dz. Okay, so we'll have our minus k dx dy into del 2t del z squared dz. And so if we add up all this to get our total flow, total dq, that is q, total, we are going to have minus k dy dz dt. Remember we have dx, so we can put our dx there also. dt del t del squared t del x squared. Then we have minus, so we have handled that. So let's handle this particular one. We minus k dx dy dz. Remember that, now we have factored it in there. Del 2t del z squared. And of course, now we are left, we have jumped one. We want to put in this one first. We have rushed it a bit, so we have skipped this one. So let's go back to that one. Of course, it will be the same thing, del x, del y, del z, factor in y there. So it's taken care of. It will be del 2t del squared y squared. And then the last one will now be minus, that is, now we have sorted that, this one, sorting that out, now will be minus k dx dy dz into del squared t or del z squared. So we can again factorize these quantities here. We have minus k dy dz dx. That's in 3 dimensions. 1 dimension will be talking of either the x-axis or the y-axis or the z-axis. So it's 3 dimensions, so we have all the axis x, y, z that are indicated. So q therefore is equals to minus k dy. Let's start now, let's be more orderly. Dx dy dz into del 2, del squared t, del x squared. This is now plus del squared t, del y squared, plus del squared t, del z squared. Very important for us to note that. Very important for us to note that. So, the case of steady state flow, the overall sum should be 0. Q will be 0. Q will be 0. So that basically we have del. If Q is 0, of course, we can divide that 0 with this, so we'll be left with del squared t, del x squared, plus del squared t, del y squared, plus del squared t, del z squared is equals to 0. So there's a very interesting and important quantity which has come here, which we call the Laplacian. It's the Laplacian of t, called the Laplacian. And it can be denoted as del squared or just del. You can denote it as del squared, the inverted del, delta, squared, or just leave it as del. And so the Laplacian of the t in this particular case is we can either del squared t or del t is equals to 0. And one important aspect of this Laplacian is that it doesn't depend on the coordinates. It doesn't depend on the coordinates. The Laplacian there is not dependent on the coordinates. Very important thing to note about the Laplacian. Which you say can be del squared or it can be delta, is not dependent on coordinates. In fact, we refer to it as being translationally and rotationally invariant. We say it's translationally and rotationally invariant. So the Laplacian for the temperature there, which has to do with the heat, is actually 0, as you see that for the steady state, which we had. Remember, we had said Q was minus K dx, dy, dz. Then we had into the Laplacian, d x squared, del squared t, y squared, plus del squared t, del z squared. And so we have that is Q minus K, the thermal coefficient, into the Laplacian, which you can write T. Or you can leave it as Q minus K. I want to just make sure you are familiar with notations. And that Laplacian, very important, is independent of coordinates. So, I repeat, when we're dealing with one dimension, we're talking of heat transfer along that axis. And we're assuming that those planes which are normal to that axis are all isothermal, just like we have said in our earlier lectures. But in 3 dimensions, we are dealing with a temperature field. So if in this temperature field, think of it, in that temperature field, let us say, temperature field, and you have T1, some point is T1, another one is T3, another one is T1 here, another one is T2, then another one is T4, another one is T1. Then in that particular case, if you join the T1s, then that will be isothermal. So that, for example, you can coin that temperature field, like we can have a situation where we have this as isothermal. You see, this is isothermal. Then we have the heat flow. And of course, you can have more isothermal. This could be the heat flow. So we are dealing with a field. We are dealing with a field, a temperature field, where during those points to the same temperature, those are isothermal. So for that, we say that the material needs to be homogeneous. In other words, its specific heat, its density, and thermal conductivity. The material should be relatively uniform. And we said it has to be isotropic so that a given property is the same in all directions in that material. So let's stop at that particular point. We'll continue our lectures in the next series.